Today we'll dive into support vector machines. Unlike other models we've considered, which in one way or another look at actual probabilities, either by estimating them class by class, as with generative models, or by trying to directly estimate conditional probabilities of each class from the classes jointly, as with logistic regression, support vector machines are based purely on geometric considerations. The idea is that we want to separate the classes as much as possible, much in the way that your eye would. So let's look at an example. So suppose we have some blue points here and some orange points here, and we want to be able to say for a new point based on its feature value, so its x value and its y value, whether it's blue or orange. So if it shows up over here somewhere, we'd probably say it's orange. If it shows up over here, we'd say it's blue. And if you're doing this problem with no prior training, probably what you would do is put a line through here somewhere, splitting the orange from the blue, and on one side you'd say blue, and on the other side you'd say orange. And in fact, that's exactly the idea of the support vector machine. So we get a line like this. And if we start thinking about what it is that makes this line better than alternatives, like maybe sliding the whole line down while preserving its slope, or maybe making it more vertical while still separating the points. The issue is that this point has a bigger minimum distance to the two classes. So if we ask what's the closest point, either orange or blue, to the separating line, this one is the one that's going to have the biggest value for that. So we move it too close to the orange, there'll be an orange point closer. If we move it too close to the blue, there'll be a blue point closer. This one kind of stays away from both as much as possible. And one kind of elegant way to organize that is to thicken the line into a slab. So a slab is going to be a set of points between parallel lines in this case. So for example, in this picture, it might look something like this. And then we can just say that the decision boundary is the midline of the thickest separating slab. So you have this slab separating the points. It's as thick as it can get. We can't sort of jimmy it by turning it a bit to get it any wider, and we certainly can't just widen it. And so the midline here is going to be the line that we want to select to separate the orange from the blue. So we have to start thinking about how to set this up mathematically if we want to compute it. We want to tell the computer that the slab needs to actually separate the points where all the ones in one class are on one side and all the ones on the other class are on the other side. And then we need to get it to tell us how to make the thickest one. And there's a standard way to do this. There are various ways you could go about it, but this one turns out to be the most useful. The idea is that these lines, both the midline and the edges of the slab, are level sets of the same linear function. So you can tell that just because they're parallel to each other. What we're going to do is describe this linear function as beta transpose x plus alpha, where x is the feature vector, beta transpose is a vector of coefficients, and alpha is a constant. And what we want to do is choose beta transpose and alpha in such a way that these three lines are the -1, 0, and +1 level sets of that function. Let's take a look at what that's like. What we can do is adjust the value of alpha to see how that changes things. It just slides the level lines around. And we can also adjust the values of beta. So if we preserve the direction but increase the norm of beta, then the level lines get closer together. And that makes sense because the gradient of the function that maps x to beta x plus alpha is just beta. And so the norm of the gradient is the norm of beta. So it's going to be a steeper function with closer together level lines if we ramp up the norm of beta. We can change the direction of beta to get the line to have a different angle. We can flip it around the other way by making the two components of beta have opposite signs. And once again, we can shift the positions of the lines with alpha. So we end up with this very tidy picture where our slab is defined to be the set of points where beta x plus alpha is between -1 and 1, and the thickness of the slab is controlled by the norm of beta. And the direction of the line is controlled by the direction of beta. So this perpendicular to the level sets is equal to the gradient, which is just beta. And finally, alpha can be used to translate the slab to the appropriate place. So the problem we're facing here is a constrained optimization problem. What we'll do is encode the classes of the points as +1 and -1. And then what we can see from the picture is that if the slab actually does separate plus or minus, then beta x plus alpha for each of these training values x needs to be greater than or equal to 1, meaning that that point is on this side of the slab. Likewise, the beta x plus alpha values for each negative training point need to be less than or equal to -1 so that they are on this side of the slab. So we want to maximize the thickness of the slab, which is to say 2 over the norm of beta, subject to the constraint that the red points are all on the red side and the blue points are all on the blue side. So we get this constrained optimization problem. Maximize 2 over the norm of beta subject to yi times beta xi plus alpha being greater than or equal to 1. So what we've done here is leverage the fact that we're encoding the classes as +1 and -1 to make these two inequalities into one inequality. By multiplying by yi, we make all of the desired values for beta x plus alpha be positive. So we want beta x plus alpha to be positive when the point is +1 and negative when it's -1. But if we multiply by the class value, then we can just say we want that new value to be greater than or equal to 1. And what we're going to do is replace this objective function to maximize with this objective function to minimize. So maximizing 1 over the norm, or 2 over the norm, is the same as minimizing the norm itself, which is the same as minimizing the squared norm, which is the same as minimizing 1/2 times the squared norm. And this half is here just for convenience later because we're going to take a derivative. And we'll sort of catch that too. So this is our optimization problem. And we'll just encode it in the computer using JUMP, which is the main constrained optimization library for Julia, and get the computer to find the optimizing slab for us. First of all, we're declaring a new type to represent a support vector machine. And it's going to have fields for the training features and the training labels that were used to train it, together with the alpha and beta values that it finds. And we're also giving it these 2 other fields so that we don't have to create a new struct later when we introduce them. So just ignore C and eta for now. They're not relevant. They'll just be sort of extra baggage sitting in this struct. But then when we need them, they'll already be there. And just to be able to initialize a support vector machine with the 2 main arguments, the training features and the training response values, what we'll do is define this constructor method that just puts bogus values in these last 4 fields. And then we'll define a new method that goes through and populates those values appropriately. So our job is to write this fit function. So we'll start by initializing a model in JUMP using the IP-opt optimizer. And we set print level here to 0 because otherwise it's quite verbose. So we'll declare a variable associated with our model, actually 2 at once, which we'll call beta1 and beta2. And this is the syntax for doing that in JUMP. You just put an array here. So the idea is that this variable macro takes as its first argument the model to associate the variable with, and the second argument is the variable name. So we'll also want an alpha associated with our model. And then what we're going to want to do is add a constraint to the model for each training point. So given a particular training point x comma y, we want to say that y times beta transpose times x plus alpha is greater than or equal to 1. But we want to do that for every training point in the data set. So what we want to do is loop x comma y over the set of values that they should take on. So the set of y values should be just the response values for the training set. So that's s dot y. And the x values should be the rows of the matrix containing the x values. So in Julia, you can just do each row. And here we're looking at the x and y value associated with this support vector machine. So we'll initialize it in such a way that contains its x and y. And then we'll be able to use them in the training process. So there are other ways you could do this, but we're following the pattern of scikit-learn since you'll be using that library a lot, and it's also influenced the Julia libraries for machine learning quite a bit. So what we'll do is zip these 2 lists so that we can make x and y take the corresponding values of the lists in tandem, and we'll add a constraint for each row that is exactly what we want. So this constraint is just saying the points need to be on the correct side of the slab. So now we need to add an objective function associated with the model. We need to tell it that it's a minimization problem. So this is not a variable value, by the way. This is getting consumed by objective, the macro, before it ever gets evaluated. So that's why it's not a symbol or something or a variable that we've otherwise defined. And the value we're trying to minimize is 1/2 the norm of beta squared. So we'll just write that as beta transpose times beta. Once we've set up an optimization problem in JUMP, we actually optimize it by calling optimize bang on it. And then we can extract the values from the variables in that model using jump.value. And since beta is actually a vector of variables, we need to broadcast this function over it rather than just calling the function. So there's this extra dot here. So this is a different dot than this one. This is just saying get the value function associated with the jump module. This one is saying broadcast that function over this array so that it's being applied to each element of the array. And then lastly, we'll just put nothing on the last line so that when we call this function, it doesn't return the value that's otherwise evaluated on the last line. So we fit our model that's assigned the appropriate values to alpha and beta. And now we can plot it, and it looks like this. So everything over here is safe red. This is on the red half of the slab. This is on the blue half of the slab. And over here we have the safe blue side. And of course, the model has done a very nice job of fitting it. It's at 2 blue training points on this side and 1 red training point on this side. and these vectors are called support vectors. And we can compare to what we did when we eyeballed it, and what we see is that we had our slab a little too narrow because we were taking the kind of edges of the points a bit too seriously, and it's also angled slightly wrong. So there's one significant problem with the hard margin SVM. If the data are not separable by a hyperplane, then the optimization problem has no feasible region. So if there's a blue point inside what's called the convex hull of the set of red points, so that's just the smallest polygon that contains all the points, then there's not going to be a way to separate them, and we're going to have to pay an infinite penalty for that point that's in the convex hull of the set of red points. And the idea of the soft margin SVM is to not be so harsh about these misclassifications. Rather than paying an infinite penalty for a point that's not on the right side of the slab, what we'll do is we'll penalize it based on how far it is from its edge of the slab. And the units we'll use for this are just the half widths of the slab. So for example, this point is 1 half width, 2 half widths, about maybe 2.9 half widths from the safe edge of the slab, from the edge corresponding to its color. So it's going to get a penalty of 2.9 here. So we just fold that into the objective function, and we're also going to include a constant so that the penalty is actually proportional to this number of margin half widths rather than being equal. And that will allow us to trade off the slab thickness consideration from the incorrectness penalty. What we need to do is sum over all the training observations. Let's index them by I from 1 to n. And we need to say for that particular yi value times beta xi plus alpha. If it's greater than or equal to 1, then just contribute 0. That's a safe point like this one. We should get nothing. And if it's less than or equal to 1, then we're on the wrong side of our edge of the slab, and we should pay a penalty proportional to that distance from 1. So we're going to subtract this value from 1 to get the distance from the edge of the slab in the wrong direction. And then we'll compute the positive part of that. In other words, if it's negative, that means it's fine, return 0. If it's positive, then we need to count that, so we keep that value. So this subscript plus operator just returns the actual value for positive numbers and 0 if the number is negative. So it's customary here, and we'll see how it's useful in a minute, make up a new vector called zeta, whose ith component is just the penalty paid for the ith training observation, and then translate this minimization problem back into a constrained minimization problem. Then the second term here will be c times the sum of zeta, and we're going to write the sum of zeta as the dot product of zeta with a vector of all ones. So this blackboard bold 1 here without a subscript is going to mean a vector of all ones of whatever length it needs to be for the operation to make sense. So in this case, the length will be the number of training observations so that we can dot it with zeta. And so the constraints we need to put on zeta in the context of this problem to ensure that we actually get the same value that we wanted to have in this unconstrained problem is that the components are all greater than or equal to 0, and 1 minus x beta plus alpha is greater than or equal to zeta. So that's ensuring that zeta does incur the full correct penalty for each point. Except we've made a mistake here because the way in which y is multiplying by x beta is a little bit unusual. It's a point-wise multiplication operation. As you can see here, each component of y just directly multiplies the corresponding component of x beta plus alpha. So we're going to make up a new piece of syntax for this, which is an O with a dot inside. So that just means point-wise multiplication. In Julia, that's going to be point asterisk, as opposed to this ordinary multiplication, which is just an asterisk. And sorry, I actually turned around this inequality. It should be less than or equal to. So if we want to set up this optimization problem in JUMP, we'll follow the same idea. We have this piece of boilerplate to set up our model with the IPOpt optimizer. The other thing we should do here is assign this C value that's being used to train the model to the C field of the SVM. We had that C field there for this, so let's do it. S.C equals C. Okay, and now we just set up our problem. So a lot of it is the same as before. So let's start with what we had before. So we have beta and alpha, those are all the same. We're also going to need another variable for zeta. And there are as many zeta components as there are training observations. So that's the size of the X matrix in the first direction. So that's the number of rows in the matrix X. And let's graduate from this for loop constraint and vectorize it. So now, rather than representing an individual value of y, y is going to represent the whole vector. So let's call it s dot y. That's the training response vector coming from the support vector machine. And now when we multiply, as we said, it's not an ordinary multiplication, it's a pointwise multiplication, so we need dot asterisk. And then here, instead of beta transpose times x, it's going to be x times beta. So that's the appropriate vector form of calculating beta transpose x for each row x. And then again, this is a pointwise operation, this addition of alpha. We're doing it to each entry, so we should put the point in front of that as well. And again, this is a pointwise comparison. And we decided that instead of comparing to 1, we're going to compare to zeta and put the 1 on the other side. So this is just a Julia translation of this inequality, 1 minus x point times x beta plus alpha greater than or equal to zeta. So that's what we have here. And then the function that we're going to minimize isn't 1/2 beta transpose times beta, that plus c times the sum of the entries of zeta. And we could write that in the cute way we did notationally as a vector of 1s dotted with zeta, but we can just directly write sum. And that's a little more clear. And we messed up here because we forgot to add our constraint that zeta is greater than or equal to 0. And then we messed up again because actually this is supposed to be less than or equal to. So we got the same result. And what that's telling us is that this c value is large enough that it would rather just get all of the points right than pay the penalty for having one of them a little bit wrong. What we can do to get a different result is lower the value of c a little bit. And then the optimization sees fit to widen the margin and just pay the penalty for some of these points not being quite right, because it's paying such a small penalty per point. So here, all of the training observations are actually inside the slab at this point, because C is so small. It's not even worried about paying this penalty for all of these points. It's trying to get the slab wide. In problem 3, we'll take a different perspective on the problem that involves a little bit of math theory. And what's going to come out on the other side is tremendously practically useful. In fact, most often when people compute support vector machine solutions, they're going to be using this formulation we're about to derive rather than the original one. And we'll see the advantage of using this new formulation next time. So here's the idea. We have 1/2 beta squared plus c times the sum of the zeta entries, subject to 2 constraints. One of them that this value is less than or equal to 0, entry by entry, and the other that this value is less than or equal to 0, entry by entry. So what we'll do is define this function h, which returns infinity if it sees any components which are positive, and returns 0 otherwise. So if we plug in a feasible collection of variables, then it will return 0, and we'll be back to just optimizing these first 2 terms. And if we plug in something infeasible for either one, it returns infinity, and we won't be able to get any sort of meaningful minimum, because no matter what these values are, when they add to infinity, they're going to give infinity. So it doesn't seem like we've done much. We just come up with a piece of notation to put the constraints into the objective function. But then what we can do is introduce these other variables. We're going to call eta and theta. And the idea is this function h, which we can't really meaningfully graph, but I'll write something here. So there's this infinite discontinuity where it's fine if it's negative or 0, but then it jumps up. It says this infinite discontinuity, and it's just equal to plus infinity after that. Imagine that it's just all the way up, so to speak. The idea is that if we consider the set of lines passing through the origin and having positive slope, and let's call that slope lambda here. So this is a function lambda times x. Lambda times x is always less than or equal to h of x if lambda is positive. So ratcheting lambda down as small as possible, we just get this horizontal line, which is less than or equal to the red one. And of course, if we increase the slope, we'll never reach the red value over here, and we're always below on the left side. All of these green lines are less than or equal to the graph of the red function. Furthermore, what we can say is that point by point, h of x is actually equal to the maximum possible value of any one of these green lines. So the green lines can get as steep as possible. So over here, if we plug in an x and we ask what's the biggest lambda x we can get, well, we can get one as big as we like. So we'll just say the maximum is infinity. If we plug in an x over here and we ask what's the biggest lambda x value we can get, it's going to be 0, because a positive lambda value is going to return a smaller output. So we run with this idea that h of x is the same thing we get if we take the maximum over all values greater than or equal to 0 of that value times the input. So that's what we have here. We introduced for every component a new value, let's say eta I, and we package those together into a vector called eta, and then we dotted that with this vector. And if we take the maximum as eta ranges over the values that are in every component greater than or equal to 0, then we're going to recover this value. And same idea over here. So it still feels like we haven't done anything because we just put the constraints into the objective function with this kind of harsh function h, and then we softened h somehow by replacing it with these lines, but now we have this maximum in there, and that seems like maybe that's worse. But when we have a minimax problem, so where we're computing the minimum over some parameters of the maximum over some other parameters, and if the function inside is convex, as this one is, because everything's linear except this quadratic piece here, then there's a theorem called Slater's theorem that we won't get into the details of, but the point is, if it's a convex problem, you can swap the min and max. And this is going to give you a new problem, but once you solve this problem, it does give you the optimizing value for the original problem. So we perform this swap of this min and max, and this simplifies the problem a great deal because now we can think of eta and theta as being fixed for purposes of calculating this inner minimization. And then we can think for that minimizing point, alpha, beta, zeta, what are the eta and theta values that make its resulting objective function value as large as possible. So what we're going to do is take this expression and kind of rearrange the terms in this way, line by line. So right now we're thinking about this minimization problem on the inside. So eta and theta have been fixed. And we're just going to look at this term and think, we're the minimizing agent. We're going to try to make this term as small as we possibly can. And it actually feels too easy. Like, let's say eta transpose y turns out to be 7. So then we're looking at minus 7 alpha, and we're trying to make that as small as possible. Well, we can just make alpha really huge, and then we're going to get -7 times a huge number, which is going to be hugely negative. And we're not constrained here. We can make alpha whatever we want. So we can make this as small as we want, and the minimum is going to be -infinity. So at that point, it really doesn't matter what happens with these other two terms. They don't involve alpha, and we can ratchet this term down as hugely negative as we want. So we're always going to have no lower bound here. In other words, a minimum of -infinity. Unless, and there's only one escape hatch, if eta transpose y works out to be 0, then we actually can't control the value of this term at all with alpha. It's just always going to be 0. So if it's anything but 0, then there's going to be a way to run this whole term to -infinity. But if it's 0, then we're fine. So this outside maximizing agent, seeing that the inside minimizing agent is going to be able to achieve arbitrarily large negative values, is going to choose eta in such a way that eta transpose times y works out to be 0. It's going to have to, because otherwise it's going to get a total maximum with -infinity, which of course is undesirable to the maximizing agent. Likewise, with this term on the second line, if any component of eta plus the corresponding component of theta works out to be anything but c, then in that component we're going to get a non-zero coefficient here. And once again, the minimizing agent can take that corresponding component of zeta and make it really huge positive or huge negative, depending on the sign of the factor it's multiplying, and get a huge negative value. So once again, this outside maximizing agent is going to have to choose eta and theta jointly in such a way that its components add up to c. And that way, this whole vector will be 0, that whole term will be 0 regardless of what happens to zeta. So then the minimizing agent is just going to minimize these first 3 terms, and that's going to give you the resulting critical point where you achieve the maximum for this minimum function. So we're down to just finding the beta that minimizes this first expression, because if you notice, there's no alpha or zeta here in this first line. And that's going to be a vector differentiation problem. So this term doesn't involve beta, so its derivative is going to be 0. This one we've seen before, it's just beta transpose. For this second term, we have to account for this weird dot operator, which we haven't dealt with before. But the point to make is that when you pointwise multiply 2 vectors and then dot with a third vector, what you get is this sort of 3-way dot product, where you have eta 1, y1, x beta 1, plus eta 2, y2, x beta 2, and so on until you get to the last component, eta n, yn, x beta n. And this makes it clear that these operations associate. We could have pointwise multiplied these two and then dotted with this vector, or we could have done it the other way and pointwise multiplied these two and then multiplied the resulting vector with this vector. And in this form, we just have derivative with respect to beta of something times beta, and that's just going to be that something. So if we set this expression equal to 0 and solve, we're just going to get beta is equal to x transpose times eta multiplied pointwise by y. And I noticed I made a mistake here. this should have a transpose, as should this one, because we're multiplying this vector by this one, so this first one should be a row vector. So if we substitute back in, we end up with this objective function to maximize. And recall, we still have the constraint that eta transpose y has to equal 0. In other words, the eta weights corresponding to the positive training observations have to add up to the same thing as for the negative training observations. And we can drop theta out of the picture by noting that its values are forced by the values of eta by the constraint that eta plus theta has to add up to c in every component. So the only way in which it shows up here is that eta can't get bigger than c, or else theta can't be non-negative. So we're given some code here to plot the values of eta alongside the actual point so we can see what's going on. So what we see is that we get a bunch of zeros over here on the blue side, a bunch of zeros over here on the red side, and then all of the vectors that are inside the slab or on the wrong side of the slab get a value of 0.1, and that was the c value that we used here. We can adjust the c value in a minute and see how that changes things. The only eta values that can be anything other than c or 0 are the ones that are exactly on their side of the margin. So you see a 0.03 here, 0.07 here, and everything else is a 0.1 or a 0. So we change the c value, we'll get a different fit, but the same idea. So the margin, so the slab gets narrower, and we get this 0.17 value, so that's between 0 and 0.5, but it's right on the boundary. Same idea. There's going to be a point here where you get a value of 0.19 that's exactly on the boundary. Every other eta value is either 0 or 0.5. So lastly, let's look at a high-dimensional real problem. So we're going to look at the MNIST digits again, the ones that are either 0 or 1. And by the way, this ref thing is just what you do in Julia when you want to protect something from broadcasting. So we want to say entry by entry that the corresponding label is an element of the set 0, 1. But if we do it that way, this broadcast operator is going to see that 0, 1 is iteratable, and it's going to try to broadcast it with this labels vector. So we need to say, no, this thing is really just treated as an atomic single unit that's not being broadcasted at all. And then everything works fine. So we pull in our data, we reshape our features so as to serialize the images. Otherwise, each training observation is a matrix rather than a vector. So we can look at one of them here. So that's a 0. And what we want to ask in this question is it the case that these data are linearly separable? Is there a hyperplane in this 784-dimensional space that separates all the zeros on one side from all the ones on the other side? So on one hand, we have a wide variety of different images, and there are a lot of them. There's a very large clump of zeros and a very large clump of ones. There's about 6,000 training observations for each type. On the other hand, there are lots and lots of possible directions in 784-dimensional space along which these training observations might be separated. So it's not clear how this is going to work out until we actually compute it. And the way we're going to do this is we're going to use a library called libsvm, which is written in C, and it has bindings in R and Python and MATLAB and pretty much anything you can think of. It's a standard tool for computing support vector machines in a performant way. There's been a lot of work that's gone into choosing wise numerical methods that circumvent some of the storage problems you run into when you try to use general purpose solvers. So we didn't see that above because we were using relatively small training set, but you do run into that problem, and libsvm handles it in a nice way. So what we're going to do is just call svm train on the feature values and the labels. And we're going to use a linear kernel. So we haven't talked about what a kernel is, but the default one is not linear, so we don't actually try to separate with a hyperplane unless we include this keyword argument. And we'll use a very high cost value. So we'd like to just say do a hard margin SVM, but libsvm won't do that actually. It only does soft margin SVM. So to simulate a hard margin SVM, you have to use a high cost value. And what you'll see if you dig into it is that the model doesn't actually store all of the beta values directly. What it stores is the support vectors. So these are the vectors in this picture that have an eta value that's positive, either because it's just squarely on the wrong side or because it's right on the boundary. So this would be a support vector, but all these ones in the slab would also be support vectors, and like this one on the wrong side. So it's going to store the support vectors as well as some coefficients for those vectors. And the reason this happens has to do with this formula, because we can throw away any components where eta is 0 and still get the same result in this formula. If we just throw away the corresponding rows of the matrix X, then we get the same beta value. And ideally, if the data are reasonably separable, we are going to have many more vectors which are on the correct side than ones that are in the slab or on the wrong side. So we'll save a lot of storage that way. Anyway, this is how libsvm does it, and you can multiply the model values by the coefficient. So this coefficients vector is playing the role of this eta times y part. So it goes ahead and multiplies the plus or minus ones from the y vector by the weights that it finds, and it stores that as the coefficients. And the way libsvm works is that it stores the design matrix capital X here as a transpose of what we would usually do. So there will be one column per training observation, and the rows correspond to features. So that's why we're not transposing it here. Anyway, that's our beta value. So first of all, we need to change our image format to PNG because we're going to get a ton of points here, and we'll slow down our browser if we have too many points there with the vector graphic that it usually uses. Anyway, what we can do is calculate our feature matrix and multiply it by beta, and that's going to project each feature vector onto beta. So we're just computing a dot product, which is how you project onto a vector. And then we can scatter plot that to see the separation, and we can see visually, do we have blue points and orange points on top of each other or not? We're trying to scatter a one-dimensional thing here, so we do need to supply some kind of bogus y values. So we'll make a vector of zeros, and we'll group by the labels of the original data set. And what we see is that we do actually have separation. Not only that, along the direction where the two classes are most separated, we end up with this gap of size nearly 2 actually. It's like 1.999. Between the biggest 1 in that direction and the smallest 0 in that direction. So not only do we get a separating 783-dimensional hyperplane in this space, it actually separates quite widely. If you look in that direction, the orange clump and the blue clump are not particularly close. So in summary, the hard margin SVM looks for the thickest slab which separates the feature vectors for the two classes. The soft margin SVM institutes a penalty for points which are not on the proper side of the slab, which is proportional to the number of margin half-widths away from the safe edge of the slab. The soft margin problem can be reformulated using Lagrange duality as the following dual problem. The eta values correspond to weights, which get assigned to the points, and they're 0 whenever a point is correctly on the safe side of the slab. And it's equal to C when the point is in the slab or on the wrong side. Only when the point is right on the edge of the slab can it be between 0 and C.